Okay, so earlier we said that our special angles were angles where the trig functions would give us ratios that we would know the exact values of, right? So in the special angles we discussed were 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, 180 degrees, 270, and 360 degrees. Okay, so out of all of these, out of this entire set, we just looked at these three, 30, 45, and 60, and we identified them using the special triangles. Now, what I'm going to do now is I'm going to look at the rest of the special angles, and I'm going to show you a way to find their values. And this method is going to be through the use of a unit circle, right? So I'm going to construct, in order to look at the unit circle, we need to look at angles in standard form, right? So I would advise you guys to kind of review that video based, regarding angles in standard form. Alright, so here's our Cartesian plane. I'm going to take a look at angles in standard form. So recall that if we're looking at angles in standard form, an angle is a degree of rotation from lines or rays, and one of the rays is a reference ray that we're going to be looking at, and it's called the initial arm. It's located on the positive x-axis, right? And the other ray here is basically going to be some angle at or away from the initial arm, and this is called terminal arm. And we also stated that the vertex was 0 and 0, and then positive rotations were counterclockwise rotations, right? Now, a unit circle is a special type of it's a special type or case of angles in standard position. We know that a full rotation here, if I did a full rotation, right? You know what? I'll use a different color so we don't have to. We know that a full rotation is going to give us 360 degrees, right? And full rotation is going to create a circle. Okay, so just don't mind my circle drawing abilities here, right? But assume that this is a circle, guys. Okay, so this is a circle. So full rotation of the initial arm, the terminal arm would give us a circle, right? We also stated earlier that we can look at the position of the terminal arm from the origin, from the vertex, which is 0 and 0, as a point x and y. Okay, so you can look at this position as x and y. Now, a unit circle is a special case where the terminal arm's length, which becomes radius if you have a full rotation, the radius of this circle here is going to be 1 unit. Okay? So the radius is going to become 1 unit, right? And a degree of rotation here, call this guy theta. The degree of rotation here is basically going to create a right angle triangle, right? Because this point can be expressed as x and y, this coordinate here, this dimension here is x, and this dimension here, this dimension here is y, and this dimension here is x. So therefore, the ratios of the angles are as follows. Sine theta here is going to call this guy r, right? Sine theta here is opposite over hypotenuse, so it's y over r, right? Cos theta is basically x over r, and tan theta is basically y over x, okay? Now there's a few things you want to kind of note here. We said that this unit circle has a radius of 1 unit, so r here is 1, so because r here is 1, then we basically, sine theta is equal to y, because r here is 1, cos theta is equal to x. And just from this, you can note that tan theta is y over x, because sine theta is y, it's basically sine theta, and cos theta is x, we get tan theta is equal to sine theta over cosine theta. This is actually a really important identity that you're going to be using a lot later on. And this is, this is the quotient identity. Okay, so this guy here is a quotient identity, right? And basically tan of any angle theta is equal to sine of that angle divided by cos of that angle. Okay, so keep that in mind. So we understand that notion, but we also stated that points can be expressed as x and y, right? So using that notion, because sine theta is y and cosine theta is x, therefore points can also be expressed as cos theta and sine theta. So we can look at a position of the terminal arm by looking at the degree of rotation of its angle. Okay? Now, a few things to note here. Because we have a unit circle and the radius is 1, right? Then this point here, should be 1 and 0, because the radius from the origin, from the center of the circle to the outside of the circumference is 1 and 0. This point here should thereby be 0 and 1 if this is a perfect circle. This point here should be negative 1 and 0, and then this point here should be 0 and negative 1. So these are the 4 points that are associated with the circle, right? Now we can imagine that if the terminal arm was located at the initial arm as such, right, the angle here would be 0, right? So theta here would be 0 degrees. And the point of the terminal arm would be in the form of cosine 0 and sine 0. Now this is also equivalent to the coordinate in terms of x and y as 1 and 0. You guys see that? So as a result, we can understand that cosine 0 is equivalent to 1 and sine 0 is equivalent to 0. So these are the values associated with cosine 0 and sine 0. Let's try another one. Right, so this is when theta is equal to 0 degrees. Let's see what happens when theta is equal to 90 degrees. So if theta was equal to 90 degrees, now the terminal arm would be located here. Remember, the rotations are relative to the initial arm. If theta is 90 degrees, if it's positive 90 degrees, this is a counterclockwise rotation 90 degrees, right? So we'd expect the terminal arm to be positioned there, right? And if we look at that, then this would be relative to the angle cosine 90 degrees and sine 90 degrees. And this would also be related to its point in this x and y coordinate 0 and 1. So this tells us that therefore cosine 90 is equal to 0 and sine 90 is equivalent to 1. Okay, so those are the values for cosine 90 and sine 90. Okay, let's take a look at another example here. Okay, so let's say that theta is equal to 180 degrees. So if theta is equal to 180 degrees, our terminal arm this time would be rotated all the way here to counterclockwise rotation. It would end up there, right? And in this case, we would have, the point would be cosine 180 sine 180, and it would be equivalent to negative 1 and 0. So therefore, let's use a different color so we don't get mixed up. Cosine 180 is equal to negative 1, and sine 180 is equal to 0. That makes sense? Right? So that's basically 1/2 of a quadrant. Let's take a look at the next special angle. So we figured out values of this, we figured out values of 90, 180, let's look at 270 and 360, right? Okay, so I'm just going to erase this guy, because we'll get back to that afterwards. But let's take a look at when theta is equal to 270 degrees. Okay, when theta is 270 degrees, our terminal arm can be located here. Okay, so if a terminal arm is located there, then the point equivalent here is cosine 270 degrees sine 270 degrees, and this is equivalent to the point 0 and negative 1. So therefore, cosine, you know what, let's use blue here. So therefore, cosine 270 degrees is equal to 0, and sine 270 degrees is equal to negative 1. Okay? And for the last case, when theta is equal to 360, you can actually notice that we just get back to, if we did do the rotation from the initial arm, we just get back to 0 degrees. So it's the exact same values as 0 degrees, right? So if theta was equal to 360, right, then you'd have point cosine 360 sine 360 is equivalent to 1 and 0, and you can see that cosine 360 is 1 and sine 360 is 0, right? So therefore, Cosine 360 is equal to 1. Sine 360 is equal to 0. And this is the same as cosine 0 and sine 0. Okay, those are the values of our respective special angles: 0, 90, 180, 270, and 360.